All right, let's introduce the source-free RC circuit and discuss some of the qualities or characteristics of it. Okay, so as we see here in this diagram, we have a capacitor and a resistor, and that's where we get the RC notation or RC circuit. And a source-free RC circuit occurs when its DC source is suddenly disconnected. Okay, so you disconnected the power source, and then because the power source was on previously, there is going to be energy stored in the capacitor, and that's going to be released into the resistors. Okay, so let's write down this definition. So a source-free RC circuit occurs when its DC source is suddenly disconnected. Okay, and then what happens is the energy that's stored in the capacitor is then released into the resistor. Okay, and we'll see that when we're talking about source-free RC circuits, we're going to be starting with more complex circuits, and we're going to try to simplify them to put them in this format. So keep that in mind when we're discussing examples later on. Okay, so if we consider this circuit here on the left, it's a series combination of a resistor and an initially charged capacitor as shown. So here we consider a series combination of a resistor and an initially charged capacitor. Okay, and through here we're going to do some derivations. So since the capacitor is initially charged, we can assume that at time 0 the initial voltage is going to be V naught. Okay, let's go ahead and make this assumption. So since the capacitor was initially charged, we can assume at time equals 0, the initial voltages is V of 0 equals V naught. If we apply KCL to the top node here, if we apply KCL here to that top node, apply KCL at the top node, we get the current going through the capacitor plus the current going through the resistor equals 0. Again, the current going through the capacitor plus the current going through the resistor equals 0. Or we can rewrite this as the change of voltage over the change of time plus V over R times C equals 0. Okay, and this here is a first order equation, differential equation. Okay, and then we can integrate and come up with an equation here. So we can integrate both sides. Okay, so what we're saying here is that IC, so let me go ahead and rewrite this so we can see where we got these numbers from. IC is going to equal to C dV dt, and IR equals V over R. Okay, and that's how we come up with this, by just rearranging, plugging them in and rearranging. Okay, so we can further rearrange this equation. Let me move these guys down. So we can further rearrange the terms. So now we can say dV over V is equal to 1 over RC dt. So put the V's on one side, and then we can integrate both sides. Integrate this side, integrate this side, we get natural log of V is equal to minus T over RC plus natural log of A, where the natural log of A is an integration constant. Okay, and then again we rearrange the equation. We get natural log we get natural log of V over A is equal to minus T over RC, and then we take powers of E, so we take this E to the power natural log. So again, we take the powers of E on both sides here, and we come up with the equation V of T is equal to A e to the minus T over RC. Okay, and then from the initial conditions, we can further rewrite this equation as, and the initial conditions were that V of 0 is equal to A, which equals V naught. So then we can rewrite this equation as V of T is equal to V naught e to the minus T over RC. Okay, so that's the derivation for the voltage there. And as we see, let me go ahead and write this here, highlight this guy, come up with this equation. And that's the equation we're going to be looking at in this chart here, in this natural response that we're going to get as a result. So as a result, we get this natural response. Okay. Where this is V naught e to the minus T over tau, where we're defining our tau as our RC. Okay. RC. So what does this mean? So let me bring this up here a little bit. So the result shows that the voltage response of the RC circuit is going to be an exponential decay. Okay, so based on the initial voltage. So this is going to be initial. Oops, what am I do? So the result shows that the voltage response of the RC is an exponential decay. And importantly, it's going to be an exponential decay of the initial voltage. And so this is down here, the initial voltage. And since this response is without an externally applied voltage or current, the response is called a natural response. And this is why we're calling it, because no external voltage or current. Okay, so that's why we call that a natural response. So a couple of things here with regards to this chart. I'm going to come down here and further define this here. Going back to the tau, the speed, so we're going to say the speed at which this decays, the speed at which the voltage decays can be characterized by how long it takes the voltage to drop to 1 over E of the initial charge. Okay, so let's go ahead and write that down. Can be characterized by how long it takes the voltage to drop to 1 over E of the initial voltage. Okay. All right. And this is going to be called the time constant, and it's represented by tau. Okay. So it's going to be our time constant, and it's going to be represented by tau. This is the time constant. Tau. And if we select 1 over E as our reference voltage, then tau equals RC. Okay. So by selecting E as the reference voltage, tau, as we just defined, will be RC, and then the voltage equation can be expressed as V of T is equal to V naught e to the minus T over tau. Okay. And note, tau here is 0.36788, the voltage. Let's further talk about the RC discharge. So if we know the voltage, we can find the current. And the current is going to be I sub R of T is equal to V naught over R e to the minus T over tau. So that's another equation we can look at and use. And then the power dissipated. So this is the current, and then the power dissipated can be defined accordingly. And we're going to talk about the power dissipated in the resistor. It's going to be P of T, P power in regards to time is V naught squared over R e to the minus 2T over tau. Okay, so that's just another equation. Undo that, do it again, here. And then the energy absorbed is going to be WR, and this is by the resistor again, is W sub R in regards to time is 1/2 capacitance V naught squared times 1 minus E to the minus 2T over tau. Okay, so we've defined the voltage, the current, the power, as well as any energy absorbed. So a couple things here. The key to working with this type of situation when you have a source-free RC circuit is to start with the initial voltage across the capacitor and the time constant. With those two items, the voltage as a function of time can be known, and from the voltage, the current can be known by using the resistance and Ohm's law, and the resistance of the circuit is often the Thevenin equivalent resistance. Okay, and I will go ahead and stop here for this introduction to RC circuits, the source free. Okay.